It's finally time to put together everything that we have learned thus far in multivariable calculus. What have we done? We've done some matrix algebra, linear algebra, we've done derivatives. Now it's time to put it together and do integrals. But the story that we're going to tell is the same story that we learned back in single variable calculus. We're going to take Riemann sums, the fundamental theorem, all that and more, and put it together in a higher dimensional setting, adapting the notion of a Riemann sum to a higher dimensional domain and an integrand on that in order to make sense of an integral. But why do we want to do that? Why do multivariate integrals? Oh, this is so useful in so many different applications. We're going to see applications to surface area, where we're finally going to be able to learn how to compute surface area when it's not something rotated about an axis. In like manner, we're going to be able to compute the volume of an object that is not symmetric about some axis. We're going to be able to work with really irregular shapes. Now you might think, oh, that's only good in 2D or 3D. No way. We're going to be able to apply this in higher dimensions using the notion of an average, for example. When we're in 3D, averages are going to be really helpful in terms of making sense of centroids of bodies. And with a little bit more effort, we can do centers of mass. We can talk about mass. We can talk about moments of inertia and various other properties associated with solid bodies, where we're going to see matrices come back into play in the form of an inertia matrix that's going to help us in solid body mechanics with spinning objects about some axis, and we're going to see some nice linear algebra come into play there. But there's going to be more than 3D when we turn to applications in probability, where many of the most useful applications of integrals reside. We're going to leverage what we know about probability density functions in one dimensions, such as Gaussians. We're going to be able to extend notions such as mean and standard deviation to the higher dimensional setting, where we have multiple random variables. And we're going to keep track of all of those random variables, again, using that wonderful tool of matrix algebra. All of these applications are going to motivate us to learn some new coordinate systems, spherical, cylindrical. In turn, that is going to help us tie together everything that we have learned in multivariable calculus. We're going to end our story with some applications to data science based on high-dimensional geometry of spheres, using everything that we've learned about integrals to tie the story together. Now, this is going to be a lot of integration, and it's going to be a lot of work, but it is going to be so much fun. There is so much waiting for you to learn about integrals.